Hey, I'm Runson Fung from USTC. I'm excited to present our work, NVTC, Nonlinear Transform Coding. In theory, vector quantization is always better than scalar quantization. However, recent methods based on nonlinear transform coding overlook the VQ advantages, space filling and memory advantages. We find that even for an isotropic Gaussian distribution, NTC cannot learn to approximate hexagon-like quantization cells. Moreover, NTC's decorrelation capability is insufficient as source correlation becomes more complex. We introduce 3 key points to design a practical vector quantizer, including 1. A multi-stage product VQ, 2. Nonlinear vector transform, and 3. Entropy-constrained VQ in latent space. Compared with previous neural image codecs, the proposed method offers superior rate distortion performance, faster decoding speed and smaller model size. Uniform scalar quantization rounds each element of the scaled vector x into the nearest integer, ignoring the correlation between different elements. Vector quantization maps the vector x into a code word with the minimal distance, which is more optimal in road performance. However, the VQ complexity increases exponentially with rate and dimension, limiting the practical use of VQ. To remove the redundancy between the scalar components of a vector, transform coding introduces a transform before quantization and an inverse transform after quantization. Despite the low complexity of transform coding, the linear transform perform poorly on nonlinear correlated sources. Vector transform coding proposes to first employ transform between sub-vectors and then vector quantize each sub-vectors independently. Although the redundancy inside each sub-vector is removed by VQ, the redundancy between sub-vectors still exists due to the limited decorrelation ability of linear transform. The complexity of entropy coding is also too high for practical application. Recently, thanks to the progress of deep learning, many image coding methods-based nonlinear transform coding have achieved great success. NTC replaced the components in transform coding with nonlinear neural networks. However, NTC overlooked the VQ advantages due to the use of uniform scalar quantization. Here we compare the quantization results of SQ and VQ on 3 different distributions: isotropic Gaussian, banana and boomerang. Blue line is the quantization boundaries and orange point is the quantization centers. We find that even for a simple isotropic Gaussian distribution, SQ with nonlinear transform cannot learn to approximate hexagon-like quantization cells, where the hexagon is the polytope with the best space-filling properties in 2D space. Under the high-rate assumption, the gain of space-filling advantage is about 1.53 decibels as the dimension approaches infinity. Following this conclusion, we experimentally provide the BDPSNR results by comparing SQ with nonlinear transform to VQ on isotropic Gaussian distributions. In addition, to reduce the redundancies of data distributions, existing NTC methods, SQ with nonlinear transform, rely on highly expensive nonlinear transform and context-based autoregressive entropy models. However, different from NTC methods, VQ has superior decorrelation ability, which is known as the memory advantage of vector quantizers. This advantage is more obvious when quantizing complex source distributions, such as the boomerang distribution, especially in the red circle area. We introduce 3 key points to design a practical vector quantizer, including 1. A multi-stage product VQ rather than a single-stage VQ to reduce the exponentially increased complexity. 2. Nonlinear vector transform rather than scalar transform to remove redundancy between sub-vectors with fewer parameters. And 3. Entropy-constrained VQ rather than unconstrained VQ to achieve superior RD optimality and joint optimization of latent space VQ models. Here is the framework overview for image coding. Following the structure of multi-stage product VQ, NVTC comprises multiple quantization layers, where quantization is performed sequentially from the leftmost layer to the rightmost layer. Motivated by the hierarchical structure in VAE-based methods, we integrate downscale, upscale layers between the quantization layers to facilitate global to local quantization. The intertransform consists of 2 fully connected, FC, layers along the channel axis and 1 activation function. The intertransform contains a depth-wise block FC layer that can be regarded as a block DCT combined with channel-wise learnable transform matrices. In practice, The initialization of VQ codebooks has a significant impact on training efficiency. We find this issue becomes more serious in the training of multi-stage VQ. Therefore, instead of random initialization, we propose a progressive initialization method shown in Algorithm 1. During the initialization process, ECVQ is replaced with VQ, and the conditional entropy model is removed. The vector quantizers are initialized sequentially. To make full use of every code word, we randomly reinitialize low-frequency code words using high-frequency code words for every delta t iterations. We compare the BD rate, decoding time, and model parameters of different methods on Click 2021 valid set. It can be observed that our method has the best rate distortion complexity performance. More importantly, compared to the recent VQ-based approach ZOO CVPR 2022 that relies on computationally expensive scalar transform and unconstrained VQ, our method has a significantly reduced model size, about 5 times smaller model size, faster decoding speed and better road performance. In Table 3, we provide detailed results regarding the encoding, decoding time of our method. It is worth noting that the encoding time is approximately twice the decoding time, which mainly stems from 2 factors. 1. The encoder needs to run with most of the VT units, where the decoder only has to execute the decoder VT units. 2. The computational gap between ECVQ encoding and decoding. We also provide ablation studies to validate the effectiveness of the proposed VT unit, latent space ECVQ and codebook initialization methods. Instead of manually controlling the road trade-off by varying codebook size, our model can learn layer adaptive bit allocation as shown in Figure 6. Thanks for your listening.